So combined probabilities, we're going to look here at Luisa and Ruby playing 3 games of pool, assuming they have equal skill, that each outcome is equally likely of them winning. So I'm going to build a sample space for this. And what we're going to do is we'll start here with the first game won by Luisa, and then we can go to the second game won by Luisa, and then we can go to the third game won by Luisa. Every time Luisa wins, it goes up. When Ruby wins, it goes down. So we can take this, and we have Luisa winning the first game, Luisa winning the second, then Luisa. This is L, L, L. This is L, L, R. Now, Luisa can win the first, but Ruby can take the second and then still have Luisa win the third, or Ruby win the third. And those both begin with LR. Then there's L and R. And those are all the cases where Luisa wins the first game represented. Now Ruby could have won the first game, so we have kind of the same thing going down here. But then it can go up with L and then up again with L. This L can go to R. We can have Ruby, Luisa, Luisa, or Ruby, Luisa, Ruby. Ruby wins the first game and wins the second game. And then have Luisa win or Ruby win. And now we have R, L, L, R, L, R, 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 L, finally R, R, R. Just like the ice cream opportunities, right? There are 8 of them. When we do 3 games, or when you have 3 ice creams, right? We have this possibilities going on of arranging. Well, let's answer the questions, which are about different outcomes. One player wins all 3 games. That happens here in LLL, no. And then RRR, that is 2 out of the 8, aka quarter of the time, but 2 of 8. Someone loses exactly 1 game. That also means someone wins exactly 2 games. So we're looking at something with 2 wins and a loss. It doesn't matter who's doing which. So somewhere where there's someone loses exactly 1 game. 1 loss for Luisa, 1 loss for Luisa, 1 loss for Ruby, 1 loss for Luisa, 1 loss for Ruby, and 1 more over here with 1 loss for Ruby. We got 6. Not the LLL, not the RRR, but 6 times. 6 of the 8. That's 3/4. So it turns out in this setup, you either have someone win all 3 games or you have someone lose exactly 1 game, and that covers the whole spread. Luisa wins exactly 1 game. So it's going to have a single L. Nope, 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 yes. So there's 1. Nope, yes, yes. There are 3. Luisa can win the first game only here. Luisa can win the second game only right there. Or Luisa can win the third game only right there. 3 of 8 though. Okay. That's actually half the times when someone loses exactly 1 game. It's the half when Ruby loses 1 game, Luisa wins 1 game. So it's not the 3/4, but it's 3/8. Ruby wins the first 2 games and loses the third. So Ruby wins the first game, Ruby wins the second, and Ruby doesn't win the third, she loses the third. That's this one only, RRL. All the others have at least 1 violation of that strategy, so she's only got 1 out of the 8. But here's how we drew the sample space in an organized way, and if you look, the first 4 are won by Luisa in the first game, and the last 4 are won by Ruby in the first game. Then these go LLRR, LLRR, and then this goes LR, 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 LR. And you're going to see something like that same kind of pattern developing when we do truth tables, when we start logic in our 3rd section of the course. Okay, Fred the cat gets wet food on 15 of 22 nights. So the probability he'll get wet food on any night is 15 of 22. This is, and you must choose one, empirical or theoretical. So you could guess, you have, I guess, a 50% chance. But if you know what's going on, theoretical is based on being the same for everyone, based on the way things always are, like the sides on a die or the number of cards on a deck. Empirical is based on how Fred behaves, how his owners behave, and a lot of other things. But it's not the same for everyone. It's needing us to know what's happened in the past. That's empirical. Steve rolls a die. The probability is higher than a 4 is 2 out of 6, also known as 1/3. This is choose one, empirical or theoretical. If someone other than Steve does it, it's going to be the same because the die still has 6 sides. 2 of those 6, the 5 and the 6, are larger than 4. So that's going to be theoretical. So theoretical relies on the way things are for everyone, and empirical relies on statistics, right? Things you look at that have already happened with specific individuals. We'll go for some more questions on this mixed bag here in homework 6. Continuing with homework 6, find the probability of doing, and in parentheses I wrote all of these together. Flip a coin for tails. After succeeding on that, is what's implied, roll 2 dice for a total of 8, and then draw 3 cards where all 3 are aces. Let's find that probability and maybe do it as a decimal to perhaps 6 decimal places or something like that. Flip a coin for tails. Ready? The probability equals 1 out of 2, heads versus tails. Roll 2 dice for a total of 8. We can go to our dice over there and find that, where we've got 36 ways the dice can show up, and the first 8 is here. There's one with a red 2, a red 3, a red 4, a red 5. Let's see. We can go red 2, you can't go with a red 1. Red 2, 3, 4, 5, and you can get a red 6. So it looks like you can get that 5 ways. If you look at what we might have to go along with the red number, we can go 6, 5, 4, 3, 2. Yeah, that's 5 ways. So out of 36, we can get 5 out of 36. You must roll a total of 8. There's 5 ways out of 36 to get that. So we're multiplying those together because what happened with the coin does not affect what happens with the dice. Now we get things that start to be dependent. The first draw out of 52 cards, there are 4 aces, so we'll go 4 over 52. Next card, there are only 51 cards in the deck. You took out one of the aces, so winners that are still in there are only 3 out of 51. And the last one, you took another card out, so now the deck holds 50. And you're only at that spot, looking for one more ace. There are 2 in there. If you successfully flip tails, then rolled an 8, and you do the first ace, now it's getting exciting. You do the second ace, it's very exciting. And there are only 2 there, so even here, even though you got that close, 2 times out of 50 or 4 times out of 100, 4% of the time, if you win the first 4 steps, will you succeed on that last step? But let's see what this does in terms of a probability that we got. Now what I'm going to do is I'm going to look at stage by stage, what's the probability that you do it. So I'm going to multiply each fraction by the next fraction, and we'll watch it build up to a less and less likely event. First we get 1 divided by 2. So when you put down your dollar and you flip a coin, and it's tails half the time, so we're at 0.5. Now I'm going to multiply that by 5 over 36, because that's the likelihood of success on rolling an 8. So times 5 divided by 36 equals approximately 0.07, or 7% chance that you also got the 8. And now we start drawing for the aces. Times 4 over 52. 0.005, 3 and so forth, so it's like half of 1% that you survive the first ace, times 3 over 51. And this says 3.1428822, 3.14 e to the negative 4th. So that means that the first division by 10 moves in front. We've basically got 0.0003. Now, we're going to multiply that by 2 divided by 50. And at the end of all this, what the calculator shows in this mode is 1.257. And then it says e, which means the power of 10 exponent, to the power of negative 5. What that means is we'll take our 1257, and we'll begin with our decimal right here. 1, 2, 3, 4, 5 decimal. So 1, 2, 3, 4 zeros, and then 1, 2, 5. 4 zeros, and then 125. All right, so that's our answer to the first part. 0.4 zeros, 125. If we did 6 decimal places, .000012, right? The way it's looking. But anyway, we've got that to represent. Is this game worth playing to try to win $1,000? Because imagine it on a midway. It costs you $1 to play. And if you win, you get $1,000. So what happens is if we look at the expectation, we can look at each expected value, number 1, and that's at $1,000. So you multiply this by 1,000, so you get to move the decimal 1, 2, 3 places. So the expected value of that is .0125, less than 2 cents in terms of dollars. Number 2, expected value when you're playing for $10,000. A little better. It's getting 10 times the size of the prize, and now it's worth .125. So about 12 or 13 cents. Number 3, if they happen to offer it, where the winner gets $100,000 by doing it, then the value of the ticket, I'm using 100,000 after playing is $1.25. So if it's to win $100,000, the math says play. Probably not going to win, but you're probably going to lose $1. Okay. If things worked out the average way, then you would probably win this after you plunk down, I'm going to say like $80,000 on average. You'd eventually have a winner. So if everything played out the way it was supposed to, you'd have been there a long time. You'd have spent $80,000 to walk away with $100,000. But the expected value says you should give it your shot because of what the numbers work out to the average earnings, even though almost everyone certainly loses. The prize is big enough at $100,000 to make it worth it. So why? This is a no, this is a no, and this is a yes. And it's because of expected values compared to $1. Would you pay $1 for something worth less than 2 cents? Would you pay $1 for something worth less than 13 cents? Or would you pay $1 for something worth $1.25 when we're talking cash on cash? And that I also addressed during my lecture about why I don't tend to take a ticket if I win $1 on an instant lottery to give it to me as a gift, because the expected value says I'm better off with my $1. Are these things mutually exclusive? Rolling a 2 and rolling a number greater than 4. So if we write these up, we got 1, 2, 3, 4, 5, and 6. Rolling a 2 we'll put in the box, and rolling a number greater than 4 will underline. Anything boxed and underlined, if it happens even once, then they are not mutually exclusive. Are these mutually exclusive? The answer is yes, because 2 is not among the values that are greater than 4. Sorry, I should not have underlined 4 there, but still, the answer remains yes. Those are mutually exclusive. You can't have a 2 and also be greater than 4. Rolling a 6 and rolling a number greater than 3. Let's look at them this way. 1, 2, 3, 4, 5, 6. Okay, we're going to put a box around the 6 that we rolled, and we're going to underline each number greater than 3, which is 4, 5, and 6. And that is not. So this is not, because 6 is both. Or 6 is, I guess I should say, greater than 3. And therefore it's in both. You have what I call an overlap or an intersection. So intersection means that you do not have disjoint sets or mutually exclusive events. So now we're going to move on to some more combined probabilities with questions beyond 6. Roxy owns 3 dogs, 4 cats, 5 lizards, and of course a monkey. They each have equal chance of escaping the apartment. If a pet escapes, find the probability that it is a cat or a lizard. So we have 3, 4, 5, and 1. Right? A stands for 1. I'll put a 1 there for us. Okay, so what we have is the probability equals, in the denominator we have 3, 4, 5, and 1. 3 plus 4 plus 5 plus 1. So So in the denominator, we have 7, 12, wait, 3, 4, 5, right, 12, 13, okay. And let's find the probability that the escapee is a cat or a lizard. So not the dogs, 4 cats, 5 lizards. 9 out of 13. You might try and reduce it, you don't have to, but there we have it. Of the 13 animals that might get out, we wind up with 9 that are cats or lizards. There's no gizzard, no lat, there's no liger kind of situation here. So they are not having an overlap. They are not sets. They are going to be separate from that. They're going to be disjoint sets, we call them. I don't know if sets of pets are disjoint. Independent. There are events that are like that as well. But 9 out of 13, no adjustment needed for anything that's at the same time that it's being a lizard, it's also being a cat. But now in this case, we may find some overlap. I'm going to go ahead and get some totals for us here. But what this problem says is that Ed can buy a jacket or a hat that supports the Yankees, Islanders, or Giants. Here are the options. If Ed buys an item randomly, find the probability that it is, and then it begins to ask questions. So the total of all Giants items is 20 plus 65 for 85. For the Islanders, we have 15 and 35 for 50 items for the Islanders. For the Yankees, we have 40 and 25 for 65 items for sale. Now let's look at the jackets. 20 and 15 gets me 35 and 40 for 75. But at hats, we have 65 and 35 making 100, and here we have 125. So 75 and 125 clearly get me to 200 total of all the items, no matter what team they're from. Or we can go 85, 135, and 65 make 200. So there are 200 items, which means the bottom of each fraction, when we're looking at the total available items, is going to be 200. Let's go with a hat or a Giants item. So what we'll do is, for hats, we go to the 125. So out of 200. Plus, Giants items, you get 85. Now look at what this does. If we were to stop now, we would say that we have 210 out of 200, which is clearly an impossibility, that it would be more than 1, greater than 100% for the probability. But what we actually failed to account for is that in this case, we have Giants items that are hats at the same time. In that case, we've got to subtract 65 with 200. If you let the 20 stand alone for Giants jackets, then you can add it to the 125 hats, you get 145. If you let the Giants items represent 85, just pick up these other 60 and you'll get 145. So we need to get to 145. The black ones do make 210 minus 65 over 200. We get 145 over 200. And this didn't have you deciding which does it count for. Just make sure you don't count them twice by knocking out the overlap. How about Islanders item or Yankees item? We'll do this with some number over 200 plus some number over 200. And some of you might question whether I should do this. You can certainly question whether I have to do this, but let's take a look at what's going on. Islanders items, 50. Yankees items, 65. How many items are Yankees and Islanders at the same time? These are running parallel. They don't intersect. There is 0 for that. So we don't even have to do the red because these are disjoint sets. They don't overlap at all. And that will get us to 115 out of 200. And finally, a jacket or an Islander item. So I'm going to take the red off this Giants because I need a clean picture again. There we go. A jacket or an Islander item. So jacket total out of 200. Jackets total 75. Islander items, 50. And I'm ready consider subtracting anything, then at the same time that it's a jacket, it's for the Islanders. So it's an Islander jacket. And that's right here. It's in the jacket row in the Islander column, so it would have gotten counted twice. We'll take off that 15. Over 200. So, if I let the Islanders be 50, I'll go grab this 20 and 40. For 60, I'll get 110. If I let the Jackets be 75, I'll just go back and get these other 35 Islander items, which are all hats, and I'll get 110. So this needs to get me to 110. I get here 125 minus 15 over 200. And therefore, you'll see that it's 110 out of 200. And there we have it. Okay. That should wrap up homework 6.